In this problem, we have a square plate that rotates about a fixed point O. At the instant represented, we have the angular velocity and angular acceleration going in a clockwise direction. We want to determine the velocity and acceleration of point A and point B. So we know the direction of the angular velocity and angular acceleration, and we know the dimensions of the plate. So what we want to do first is draw a figure indicating coordinate systems and the directions of the velocity. Now the problem asked for the velocity and acceleration of point A and B in terms of the x, y, but the nt could be used as an intermediate coordinate system. So we have to determine whether or not that is more efficient to do the nt or more efficient to do the cross product version of the equations. All right, so we have the figure here. I have drawn the velocity direction of both A and B. So to get that direction, you draw a line from the fixed point to the point of reference, and the velocity is perpendicular to that. So in both cases, perpendicular. And we know that the velocity is always in the tangent direction, so I can put the t-axis for both points, and the n-axis points towards the center of rotation. All right, we have two versions of the fixed point rotation equations, one the nt, one the cross product version. So which should we use? What's going to be easiest? Well, in general, the nt is easiest because you don't have to take a cross product. But here in the figure, point A, we can say, oh, n is in the same direction as y. So if I get the velocity and acceleration in terms of the nt, that won't be hard to switch. And the t is in the negative x. So they kind of correlate very well. But then when we look at point B, the t has both an x and a y component, and the n has both an x and a y component. So maybe the nt coordinate equations will not work as well for point B. So we're going to use the nt equations for point A and the cross product equations for B. All right, point A. All right, we know the velocity is r omega in the t direction. So we apply that at point A. So the distance between the fixed point and point A is B. And we know that the t direction is really the minus I direction. So we just substitute that in. And then the acceleration has both a t and an n component. We plug in the appropriate values when we apply it to point A. And again, the t direction is in the minus I, and the n direction is in the positive j. All right, so that was easy enough. If we were to use the nt equations for point B, it would be more complex. All right, so let's do point B using the cross product versions of the equation. All right, so here's the general form, V equals omega cross R. We apply that at point B. So we know omega is in the minus k. We know that because of the right-hand rule. So rotate your hand in the direction of rotation, and your thumb will point in the direction of the vector. And then we want to get from point O to point B. So this is RB relative to O. So O is kind of like our origin. So if you were going to stand at O, how would you get to B? Well, you would travel C in the X and minus B in the Y. So that's what I have, C in the X minus B in the Y. And then you take the cross products, make sure you look at that and understand how you do the cross product. And then we come up with our final answer. All right, we do the same for the acceleration. The acceleration is alpha cross r minus omega squared r. And again, RB relative to O. If you're standing at O, how do you get to B? All right, so again, you would take the cross products and get the final answer. So in this way, we don't have to worry about geometry transposing the nt axis into the xy axis. It just goes directly. All right, so again, make sure you understand how to do the cross product, right? You do the right-hand rule. You point your fingers in the direction of minus k, curl in the direction of I, and your thumb will point in the resultant. And then the same, minus k, minus j, and your thumb will point in the resultant.